In the last segment, we introduced the concept of a metric space, and in this segment, we'll continue the discussion by looking at sequences and completeness. We'll start by defining sequences in a metric space, look at limits and convergence, define Cauchy sequences and link this idea to completeness, and finish up by proving Cantor's nested interval lemma, which we'll need later in our discussion of compactness. So let xd be a metric space, and let xn be a sequence of elements in this space. We say that this sequence converges to a point x if for every epsilon positive, there exists an epsilon neighborhood of x such that if you go deep enough into this sequence, all subsequent terms are within this epsilon neighborhood, and this has to hold for every epsilon positive. And in this case, we say that xn is convergent and x is its limit, and the notation for this is shown on the slide. Now, just as in the case of real sequences, xn can have at most one limit. And to check this, you just need to use the fact that the distance between 2 points is 0 if and only if they're the same point. So if you have two limits, the distance between these two must be positive, and if epsilon is small enough, then you can't be within an epsilon neighborhood of both of these points at the same time. So let's consider an example of a metric space. We'll look at the space of bounded real functions with the sup metric, and we'll take the domain of these functions to be the unit interval 0, 1. Consider the following sequence of functions on 0, 1. Fn of t is defined as t to the n. So our sequence of functions is just t, t squared, t cubed, and so on. Now note that for any fixed t, as long as t is strictly less than 1, fn of t goes to 0 as n goes to infinity. And if t is equal to 1, then fn of t is equal to 1. So if this sequence of functions were to converge, a natural candidate for the limit would be the function f of t, which is 0 as long as t is less than 1, and is equal to 1 when t is equal to 1. Now ask yourself whether the sequence of functions fn converges to f. And you can do this by considering the distance under the sup metric between fn and f for any fixed n. And you should be able to show that this distance under the sup metric does not in fact go to 0, and therefore the sequence of functions does not in fact converge to f. Next, we define Cauchy sequences. We say that a sequence xn is Cauchy if for any epsilon positive, there exists some number n such that if you go past this term in the sequence, every pair of later terms is separated by a distance less than epsilon. Another way of saying this is, if you go deep enough into the sequence, then every term is within an epsilon neighborhood of every other term. And we say that a metric space is complete if every Cauchy sequence in X converges to a point in X. Now I've left out the metric D on this slide, but it's implicit. Let's consider a couple of examples of complete metric spaces. The space Rn endowed with the usual Euclidean distance is complete. Every Cauchy sequence converges to a point in Rn. And furthermore, for any non-empty set X, the set of bounded real functions with the sup metric is also complete. What this means is that any sequence of bounded real functions that is Cauchy must converge to a bounded real function. Now let's go back to our earlier examples of a sequence of functions where fn of t is t to the n. And ask yourself what happens to the distance between successive functions fn and fn minus 1 as n goes to infinity. And you should be able to get an explicit closed form solution for this distance, and to show that it does in fact go to 0. But we already know that fn is not convergent, and so therefore fn can't be Cauchy. And you should try to prove that this sequence of functions is not in fact Cauchy with the sup metric. This example shows that the Cauchy criterion is in fact a lot more demanding than the requirement that the distance between successive terms in the sequence goes to 0. We'll finish up this segment by proving Cantor's nested interval lemma. So consider a sequence of intervals an, bn, with the property that each interval contains its successor, and the claim we want to prove is that the intersection of these intervals is a non-empty set. So here's how we do it. Now the sequences an and bn are just sequences of real numbers, and these are monotonic. An is an increasing sequence, bn is a decreasing sequence, because these intervals are nested. And these are clearly bounded and therefore convergent. This is something that we proved when we discussed the Bolzano-Weierstrass theorem. Now from the completeness axiom, we know that there exists a supremum of the set of elements a1, a2, and so on. And furthermore that there's an infimum of the set of elements b1, b2. And we also know from our earlier result that the sequence of a's converges to the least upper bound of the set of terms, while the sequence of b's converges to the greatest lower bound of the set of terms. Next, observe that a must be less than or equal to b. This is because every element of the set of B's is an upper bound for the set of A's. And so B is in fact an upper bound for the set of A's. And A is the least upper bound, so A must be less than or equal to B. And to finish up, we just need to show that the intersection of the sequence of nested intervals is just the interval AB. And you should verify this by checking that every element of this interval in fact is an element of every single element in the nested sequence, and furthermore that any number outside this interval cannot be an element of every single one of the nested intervals. Now, since this interval AB is clearly non-empty, we've proved the result we were after. If you have a sequence of nested intervals such that each one contains its successor in the sequence, then the intersection of these intervals is non-empty. And that's it for this segment.